Okay, so my name's Brianna, and my presentation was on why do volcanoes cause global cooling. So first, I've mentioned how volcanic monitoring is super important because when you monitor the volcano, you monitor it usually from the surface, and so if people are able to detect CO2 levels at the surface, it means that it's an indication of new magma entering the volcanic system, and the CO2 can be detected from pretty far away, so that's how they know like it's more towards the surface. And if SO2 can be detected, which is sulfur dioxide, it's indicating that magma is closer to the surface, which is a sign that the volcano is going to erupt soon. And in order to determine the amount of SO2, determining the amount of SO2 helps calculate the amount of magma that's supplying the volcano, and knowing this is actually good because it can help predict how explosive the volcano will be, which is part of how volcanoes can make the cooling effect, is because more explosive volcanoes actually reach the stratosphere, and it's important for cooling in order if it's reaching the stratosphere. And the height or elevation of a volcano also plays a role in if the materials will reach the stratosphere, because the cooling only happens in the stratosphere. So when a major explosive eruption happens, there's dust and ash particles, sulfur dioxide, and greenhouse gases that are all released into the atmosphere. And the dust and ash can shade the sunlight and cause temporary cooling, and it usually falls from the atmosphere naturally or from rain within days or weeks. And the size of the particle matters, which I'll get into more in the next slide. And the sulfur dioxide gets emitted into the atmosphere. It usually travels to the stratosphere, and it combines with water and produces sulfuric acid aerosols. It can reflect radiation and has significant cooling effects worldwide, and the sulfur is way more damaging than the dust and ash particles. And the greenhouse gases consist usually of water vapor and carbon dioxide, but it doesn't really change the global amounts of CO2 and water vapor that we already have unless there's intense volcanism, meaning that there's multiple volcanoes erupting at the same time. So the dust and ash particle sizes are super important because large particles usually are bigger, and so they're heavier, and so they fall out of the air quicker due to weight, so they don't have much effect on cooling. And the smaller particles usually shade and cool the areas that are directly below them. And the tiny particles are the ones that are super important because they usually make it to the stratosphere, and they travel great distances because they're so small in size, so they don't have like much weight to them, so it's easy to be blown around by the wind. And they can even travel worldwide, and they can usually stay in the stratosphere for months and cause cooling over larger amounts of areas. And the sulfur is usually sulfates, and they're more effective at cooling than ash and dust particles, which I had mentioned earlier. And the sulfate particles usually appear white, and once they make the sulfuric acid from combining with the water, they make like a haze of tiny water droplets in the stratosphere. And this is what reflects the incoming radiation back to space, and once it reflects back to space, obviously it's not reaching down here, and the light that does make it through usually gets scattered, or it makes it more like less direct and more diffuse. So when the light gets less directed and more diffuse, it becomes darker. And I remember Dr. Mayer had actually sent me an email of an article that he read. It was called like A Summer for a Whole Year, and the reason it was summer for the whole year is because volcano had erupted, and it made it so dark, and the sunlight was so diffused and like reflected that the summer was cooler. The summer didn't have much sunlight because it was all getting reflected back. And these particles can stay in the stratosphere for usually up to 3 years, usually no more, and it gets moved around by the winds. And these droplets eventually grow large enough to fall back onto the earth, which is why they don't usually stay for more than 3 years. And these volcanic materials have to reach the stratosphere in order for these things to happen, like I mentioned. And if they only reach the troposphere, then it usually falls as acid rain. And in the stratosphere, the sulfate aerosols can last 50 times longer in the troposphere. Can last 50 times longer than in the troposphere. And here's kind of an image of it reaching the stratosphere and the winds kind of pushing it that way and it falling back down. And it was saying that the different wind circulations actually have an effect on what places get cooled, because eruptions in the tropics can have an effect on climate in both hemispheres, while eruptions only in the mid or high latitudes only impact the hemispheres that they're within, because the winds traveling certain directions make the particles stay in the atmosphere or the troposphere, stratosphere in different areas, cooling different areas. And a lot of people start an argument that volcanoes actually cause global warming, and I was doing some research into it, and it was saying that the carbon dioxide released from volcanic eruptions never caused detectable global warming of the atmosphere, as they were saying that they can actually detect the global cooling where they can't really detect global warming from the volcanoes. And I thought this quote was interesting. It was saying that all studies to date of global volcanic carbon dioxide emissions indicate that present-day subaerial and submarine volcanoes release less than 1% of the carbon dioxide released by current human activities. And less than 1% is obviously very minimal compared to what the human activities are putting out. And the 1980 eruption of Mount St. Helens vented approximately 10 million tons of CO2 into the atmosphere in only 9 hours. However, it currently takes humanity 2.5 hours to put that same amount out. So they're saying that carbon dioxide gets released from volcanoes at great amounts in such a short span of time, but humans are actually putting out way more in shorter amounts of times. And basically, the effects of cooling are much larger than the effects of warming in general. And an example of a volcano that caused a great amount of cooling, and I know I'm going to mess up the name, but it's called El Chichon in Mexico, and it was in 1982, and it erupted, and it was the first major eruption that had its atmospheric effects studied using modern instruments, because before they didn't really use like modern instruments in order to detect all the different stuff that had to do with the eruptions. And this eruption wasn't necessarily that big, but it released like large amounts of the aerosols, and the aerosols are what make the cooling actually happen and be so effective. And the sulfur dioxide that was ejected into the stratosphere was converted into sulfuric acid within only 6 months, which is a pretty short span of time. And a month after the eruption, there was still 20 million tons of sulfuric acid remaining in the atmosphere, which is a great amount. And this eruption is what actually made scientists realize that the sulfur dioxide is a lot more intense than the ash and dust particles that they had originally thought was what caused the global cooling. And 2 months after the eruption, the northern hemisphere was about 0.2 degrees Celsius less than the previous. And those are just 2 pictures of the eruption. And another one was Mount Pinatubo in the Philippines, and it was an eruption that happened in 1991. It was the second largest eruption of the century. It produced the greatest volume of sulfur dioxide ever measured, and it was 3 times more than the previous volcano I had mentioned. There was nearly 20 million tons of sulfur dioxide that was injected into the stratosphere, and it was circling the globe within just 3 weeks. And it said the Pinatubo eruption increased aerosol optical depth in the stratosphere by a factor of 10 to 100 times more than normal levels measured prior to the eruption, which aerosol optical depth is a measure of how much light airborne particles prevent from passing through a column of the atmosphere. So when it's increasing, it means it's harder to see through it, which is what causes like the light going back up. And this gas cloud produced from this volcano dropped temperatures temporarily from 1991 to 1993, which is 2 years following the eruption, about 0.5 degrees Celsius, which was more than twice the amount of the El Chichon eruption. And the colder temperatures actually slowed the sea level rising caused by global warming, which I have a graph to go with that too. And there's a picture of it, and then on the right, it's a distribution of the stratospheric aerosols between June 14th and July 26th. And so this is like a picture of like the aerosols like traveling and circling around the Earth after the eruption. And here's a graph showing in 1982 the El Chichon eruption, and then in 1991 the Mount Pinatubo one, and then it shows how much the temperatures dropped after those eruptions happened, which I was kind of confused because a lot of the pictures had numbers like on the y-axis that were like different than all the articles I was reading were giving me. And then there's 2 more drops over here, which indicate 2 other volcanoes that happened that were smaller intensity, and one was in Chile, and then the other one, I don't know how to pronounce it.
Sergio.
Yeah. And then this one was the global optical depth that I was talking about, and you can see from the Pinatubo one, the global optical depth went all the way up to here, and then this one went up to here. And that makes sense because the Pinatubo had so much more sulfur released from it, so it's twice the amount. And then this was the sea level change that I was talking about, and it basically like after each volcano there's like a slight like up, and then there's like a big drop down. And it was saying that water disturbances due to volcanoes cause immediate rise in the sea level, and then they drop because of the ocean densification. And the ocean densification is because there are lower sea temperatures. So lower sea temperatures make the density like change, so the water temperatures automatically or the sea level automatically goes down. And those are my sources.